Hey guys, this lesson is going to discuss some basics on inverse functions. This is just for the Algebra 2 level, and you'll explore this concept more in the upcoming, math classes if you take any. So we're going to start off with the 5 basic concepts of inverses. So the first one, and it's really the crux of everything here, inverses switch your x and y around. So your input becomes your output and vice versa. So because the x and y switch, that means that the domain and range will switch. So if your original function has a certain domain, that becomes the range of the inverse function. This one's a little weird, but we'll show you later. In order to graph the inverse, you can reflect it about the line y equals x, which is called the identity function. And once we look at the graph of that, that makes a little more sense, knowing that we flip-flop the x and y around. That's why it reflects across the line y equals x. This fourth one's really weird, but we'll look at it. The inverse is a function if the original passes the horizontal line test. We've talked about the vertical line test before. Now we're going to talk about the horizontal line test. And then the fifth one is about compositions. Basically, if you put two functions inside of each other and they are inverses, they undo themselves. So they just give you a result of x. So like this function might add 2, so then his inverse function would subtract 2. They basically just mathematically undo each other, and that's really the idea for inverse functions and why we need them in math, is because we have to have a function that undoes another function when we're trying to solve equations. So this first example, this is just a relation, a set of ordered pairs. It's written in a t table, an xy table, and they want the inverse. Well, literally all you do is you switch the x and y. So all of these y's flip up to the x row. So I'm going to put them in the same order so they match up properly. And then similarly, your x's are going to become the outputs in the inverse. So the only thing you got to be careful about is that you write them down in the exact order, because the ordered pairs should still be kind of matching up. So for instance, like this guy has an ordered pair of 4, -2, while the original function had an ordered pair of, you guessed it, -2, 4. So you see that flipping of the x and y indicated in those ordered pairs. So what if we have a function that is written in an algebraic sense or a function notation? So I don't want to list out every single ordered pair because this particular one is a line and I'd be listing out forever. So instead we're going to find the inverse function by doing just a few steps. Step 1, we're going to switch the x and y. I kind of think of this as like turning a function inside out. And then step 2, and this is really the end, well, there's 3 steps technically. Step 2 is to solve for y. And then step 3, I'm going to say name it. Name it properly is what we're really going for here. So first step, switch the x and y around. So in your problem, instead of y equals 2x minus 4, we're going to write it as x equals 2y minus 4. And now we're going to use our isolation skills. We're going to try to solve for y, which means I'm going to first move the 4 over by adding it. If you remember doing this isolation stuff early on in Algebra 2, it comes back quite a bit. This is called algebraic manipulation, and it seemed really pointless while we were doing it, but turns out there's a lot of use for it. All right, only one more step to solve for y, and that would be to divide everybody by a 2. Now I'm going to go ahead and divide everybody individually by a 2. If you did a big fraction bar, that's technically acceptable. And then step 3. Instead of calling it y equals, because it's the inverse, the notation that we're going to use is a little -1 in the exponent position. So that stands for inverse. That's the notation for inverse. So the inverse of y is, and I'm going to simplify, instead of x over 2, I'll write 1/2 x, and then instead of 4 over 2, I'll write plus 2. There, my friends, is your inverse function. So same idea here in number 3. Your first step is to switch the x and y around. So switching the x and y around, you'll get x equals -2/3 y plus 6. Now this one's a little more difficult to isolate, simply because there's a fraction, but we've handled fractions before. All right, we're going to subtract the 6 from both sides. So we have an x minus 6 equals -2/3 y. And you can get rid of the fraction coefficient in multiple steps, but I'm really lazy, so I'm going to do this in one step. I know to undo a fraction coefficient, I can just multiply by the reciprocal. So the reciprocal of a -2/3 would be a -3/2. And of course, as long as we multiply everybody by that -3/2, then we're good to go. I am going to take the time to distribute this -3/2. So this becomes, that didn't help, this becomes 3/2 x, and then you could either type this on your calculator or do a quick little mental math problem, positive 9, and then equals y. Now, it's backwards, and I haven't done step 3 yet, which is name it properly. So the appropriate name is, instead of the original y, now it's y inverse is negative 3/2 x plus 9. So there he be. Not too bad, right? So I think it was the third one on the list, or fourth one maybe, it talked about knowing whether the inverse was a function by performing the horizontal line test. Yes, on the original. So what I'm giving to you in number 6, 7, and 8, these are original functions, okay? You don't have a lot of experience with inverse functions, so you have no idea what their inverse looks like. So what I want you to make a note of on your notes is that this guy right here, this is the original. The inverse, I don't know what it looks like. Well, you don't know what it looks like. But here's the rule. If the original passes the horizontal line test, that means the inverse would be a function. Now think about that for a minute. If the original passes the horizontal line test, that means the inverse would have passed the vertical line test, which is how we usually tell if things are functions. But since I don't know what the original looks like, I have to perform the horizontal line test on the original. So horizontal line test, you guessed it, it's a bunch of horizontal lines, and you can only touch the function one time with each horizontal line. So the original, in this case, passes the horizontal line test. So what that means for us is the inverse is a function. Now notice, the original was not a function. That wasn't the question, though. It didn't say is the original a function. He fails the vertical line test. What you learn later in pre-calc next year, possibly, is that this is not a one-to-one function. That's preview to next year, okay? All right, so here, remember this weird squiggly thing, which we'll learn later. This is a sine function. This is the original. We don't know what the inverse looks like. But here's what I can tell you. When I perform the horizontal line test on the original, oh my goodness, it fails so bad. Fails. All right. Fails the horizontal line test. So because the original failed the horizontal line test, that means the inverse, whatever it looks like, is not a function. And again, this was an example where the original was a function. The inverse would not be a function. And then you guessed it, we got a third example. This one graphed for you, this is a cubic function. This is the original. But I'm curious about his inverse. So if I were to perform the horizontal line test on the original, it passes the horizontal line test. So what that tells me is that the inverse is a function. Remember, FCN is the abbreviation for function. Now, side note, the original would also pass the vertical line test. So next year in pre-calc, you guys will learn that because this particular function passes the horizontal and vertical line test, he's what's called a one-to-one function. Pre-calc's exciting. I hope you take it. All right, so a couple more examples of finding the inverse. These are just written in function notation. It doesn't get any different other than you need to remember that g of x is secret talk for y. So 3 steps, remember, switch the x and y, solve for y, and then rename it. So our first step is to switch the x and y around. So I'm going to scribble that out for a minute. So instead of y equals, we'll write x equals 5y minus 2. And then we're going to solve for y. So we're going to add 2 to both sides. So you have x plus 2 equals 5y. We are almost home free, guys, and I should have locked down that y. One more step is we're going to divide both sides by 5. Now I'm going to get a little lazy here, and I'm just going to do one of these big fraction bar divider by 5 things. So here I do have to be careful about the name. Let's go back for a moment. G of x was the original function, so his inverse is called g inverse of x. So it looks like g of x, but you stick that little -1 in the exponent position. And then I'm not going to simplify this because I'm too lazy. So x plus 2, all of it over 5. If you wrote 1/5 x plus 2/5, you are better than I. Sorry, I'm feeling lazy today. Okay, again, number 10, f of x is function notation, but we know it's secretly the output variable of y. So when I go to switch the x and y around, this becomes x equals 4 over y. And this one's a little challenging to solve for y because it's stuck in a proportion. So if you remember from last quarter, when things are stuck in a proportion, you have to kind of cross multiply them to free them up, right? So if you were to cross multiply here, you would get xy, and then equals 4 times 1, so equals 4. So I'm still trying to solve for y. So my final step here is to divide by x. So instead of calling it y, I'm going to go back to the original name of f of x and give it an inverse name. So f inverse of x, and then this is a little weird. Go and look and compare it to the original. It's the exact same function. There are functions out there where when you try to find their inverse, they're their own inverse. And if we looked at the graph of this next year in pre-calc, you guys will see this is called a rational function that has symmetry across the origin, and specifically across the line y equals x. So it keeps mapping onto itself when you twist the ordered pairs around. So like 4, 4 is 4, 4. You know, I'm making that point up, but that's the idea. So weird, right? Ugh, math, just when you think you get it. So some final conclusion ideas that we can write down for our notes. Okay, explain how to use the horizontal line test to determine if an inverse relation is an inverse function. So you draw horizontal lines on the original if each line touches once, then the original passes the horizontal line test, so the inverse is a function. I can hardly read that. All right, this is the key. So the original passes the horizontal line test. That means the inverse is a function. Oy, it's confusing, right? All right, the steps in finding an inverse. Those are those 3 steps we wrote a few slides ago. So step 1, switch the input and output. I'm just going to say switch the x and y. Step 2, solve for y. And then the 3rd step, which is really important, you're going to rename it. And remember, we're going to name it with that inverse notation. So an example would be like y inverse or f inverse of x. We saw g inverse of x. There's h inverse of x. There's all sorts of things we could be doing. All right, I think that's the whole lesson. It's a good lesson, guys. Lots of vocab, some weird concepts. It's really the foundational piece for moving on in function exploration for Algebra 2 and then beyond. And these are also good topics for the SAT. So I'm glad we had a chance to talk about them here in Algebra 2. Hey, good luck, everybody.